Welcome to this educational lecture on quantitative susceptibility mapping. My name is Steffen Bollmann and I'm a research fellow at the University of Queensland, Australia. I declare that I receive research support from Siemens Healthineers and together with Siemens have submitted 2 patents on QSM. The world is full of acronyms, which can make it quite difficult to understand a new topic. Here, I listed all the acronyms in this talk, and I hope they help as a reference when you come back to this slide. Also, throughout the talk, I abbreviated all the references I used, and here is the list of all references, so you can go back here and find the full publication I'm referring to. I also, to make this more interactive, I created a computational notebook that shows the concepts of QSM in source code. And you can play with this and hopefully this helps understanding this topic even better. So if you're interested in this, have a look at it after the lecture. Before we get started with quantitative susceptibility mapping, let's have a quick look at susceptibility weighted imaging, which is a well-known technique for exploiting susceptibility to visualize veins. SWI can be computed from gradient echo data by filtering the signal phase, weighting it by the magnitude, and then intensity projecting across slices. As you can see in the image on the right side, the susceptibility effects from the venous blood make it perfectly suited to visualize veins in the brain. So now you probably wonder, well, isn't this enough? Why bother with quantitative susceptibility mapping? Well, here's an interesting example. The question is this lesion calcified or bleeding? In this example, the SWI filtered phase shows aliasing or a dipole white-black artifact. In SWI, this lesion shows up as hypointense, so it is ambiguous. Whereas QSM shows a consistent bright spot, clearly showing that this is a blood product and the lesion is hemorrhaging. A calcified lesion would show up as hypointense in QSM and therefore allows a clear differentiation. One cool aspect about QSM is that it is sensitive to changes in any biometal, in particular iron. So it could give us a really good insight in, for example, multiple sclerosis, visualizing iron accumulation after demyelination or iron depletion from normal appearing white matter. But how can we get QSM? Well, this overview slide will guide us during the lecture today. I will start at the data acquisition and the coil combination, then show the steps that are required to compute QSM, like unwrapping, masking, background field correction, and dipole inversion. But one important note is, although I'm showing everything here in human imaging data, everything of this also works in rodents or in other animal models and also in other body regions like the liver, the joints, the prostate, and many more. So we're not limited to the brain. What is this magnetic susceptibility we are trying to measure here? It's the degree that a material can be magnetized by an external field. Here I displayed absolute susceptibility values. And water is somewhere around -9 parts per million and air somewhere around 0.36 parts per million. In QSM, we measure relative susceptibilities to water. So less susceptibility than water means diamagnetic and higher susceptibilities than water are paramagnetic. So a calcified lesion would be around -0.3 ppm in relation to water, and a hemorrhagic lesion would be around 0.6 ppm in relation to water. And these values are what you see in quantitative susceptibility maps. So here's an example from a glioblastoma patient where QSM differentiates between blood products in white and calcium deposits in black. Let's start with the data acquisition that we need to compute QSM. We know that field inhomogeneities cause dephasing, and they are due to imperfect shimming or object susceptibilities. So by measuring the complex signal of a gradient echo scan, we can compute the object susceptibility from that. Here, some considerations for choosing an imaging sequence and the settings. So as I said, we need a gradient echo sequence. A spin echo will not work. Isotropic acquisition is ideal for the inverse solution. We also want high resolution if we can, so 1 millimeter or less. Multi-echo is efficient and it can compensate some signal loss in later echoes, and we can also do a T2 star fit. So it's very nice, but not absolutely necessary. Flow compensation is a good idea, especially for the first echo. And here, a couple of examples of sequences that would be well suited for measuring QSM. There's also currently a lot of work happening in the space of accelerating QSM further and going away from the standard gradient echo, for example, using 3D EPI. And here's some work from our group that we show at this ISMRM, where we use 3D EPI with a very high resolution and get a nice QSM scan in a little bit more than a minute. Let's look at the next steps in the pipeline, the coil combination. We usually use multiple receive channels in our coils, and these different channels have unique phase offsets. So when computing a complex sum, there are signal cancellations and artifacts, and they can be seen as these zero signal in the magnitude or as open-ended fringe lines in the phase. Unfortunately, there is no simple solution because every channel has its own spatially varying phase offset caused by different factors. Some of them unique to each channel, and some of them the same for all channels. Different methods have been developed to deal with this problem, either using a single echo without and with a reference scan, or using the information from multiple echoes. The best method will depend on your MRI system and your particular setup, so here are a few considerations. Check for phase combination artifacts in your data and ask your local support for the optimal combination method that would give you nice phase data. This, of course, is less of a problem in systems with very few channels, for example, Bruker animal systems. Also, if you use Sense, this will work quite well. If you're on a Siemens system, there is C2P from Simon Robinson that helps with this problem. And there's also, on later Siemens systems, there is Adaptive Combine, which works very well. Now we have beautiful phase data, but sometimes people ask me what's wrong with their data when they see these weird lines in the data going suddenly from black to white. Well, these are phase reps, and they come from the fact that we express phase between -pi and pi. And as soon as we go outside this range, it reps back to this range. So when we go from complex to phase, this is when these reps appear. This looks bad, but it can luckily easily be restored by using a phase unwrapping technique. And we can wrap these back to the normal range. So you see that here, where we go from -pi to pi range on the left to -6pi to +6pi on the right. There are three dominant categories of unwrapping techniques. The first one, Laplacian unwrapping, works because the complex values of the true and wrapped phase are the same, and we can use this to solve this unwrapping problem. But the Laplacian unwrapping has an arbitrary background phase. So for QSM, this is not a big problem because we have a lot more background phase anyway that we need to get rid of later, and I will show that in the background field correction. But just keep that in mind. Otherwise, the technique is very fast and robust. Region growing identifies discontinuities between regions and unwraps them step by step. The problem is that this takes some time. So recent techniques like Segway are speeding this up significantly. Path-based unwrapping is guided by the quality of voxel connections. And the recent example here is the Romeo technique that's fast and works very well. Now we need to define the region that we want to include in the actual QSM computation. And this is usually not seen as that important, but it actually impacts the results quite a bit and can be tricky, especially when doing QSM outside of the brain. So why do we need a signal mask at all? Well, for most background field correction algorithms, we need to define inside outside of the object of interest. Also, including unreliable phase values in the dipole inversion will lead to artifacts. And we can see this here, where the mask is just a little bit too big on the left side, and we include values that are unstable and not reliable. And this leads to artifacts that then also expand across the whole image, because we're doing a dipole inversion and we see these streaking artifacts on the right in a difference image that then go into the whole image. So we need to do something about this. So ultimately, masking is a trade-off between excluding areas of interest and removing artifacts. We saw that in the video on the right. The bigger the mask get, the more artifacts we will get in the image, and in the end, the image is not really usable as a QSM anymore. So in my opinion, masking is not that trivial, but most QSM toolkits out there don't deal with these problems. For brain data, BET is commonly used and works well, but dedicated methods are crucial for example, abdominal QSM. And we also show at this ISMRM work from our group, where we show that it can be beneficial to use dedicated masking techniques for clinical QSM. The next step tries to remove artifacts that are caused by susceptibility sources outside the object of interest, so the background field. This on the left is the unwrapped phase. And you see that it contains a very strong artifact overlaid on top of the internal tissue field that we're actually interested in. And this so-called background field is caused by susceptibility differences between tissue and air, shim coil fields, and field inhomogeneities. And potentially also the Laplacian. If you use Laplacian unwrapping, it will contribute to this as well. So we're interested in this internal tissue field. And to remove these fields, there are different assumptions that can be made and different methods. So first group is no sources close to boundaries. This is the assumption, and the two techniques there are sharp and V-sharp. Another assumption could be that we have no harmonic internal and boundary fields, and the technique there is LBV. The last category is that we have no implicit boundary assumption, and examples there are resharp or our recently introduced deep learning-based field correction, which is called SharkNet. Off to the last step in our pipeline, the dipole inversion. Let's assume we have a susceptibility source in a static magnetic field. This susceptibility source will disturb the magnetic field in its neighborhood, and it will create this dipolar field perturbation that we see on the left. This field perturbation can be described by this forward model. The goal of QSM is to infer the underlying susceptibility source based on measuring the field perturbation. And this field perturbation can be described by a so-called dipole model, which is a simplification of the actual field distribution that happens there. And when we look again and look at the brain, we see that it's a little bit more complex. The field perturbation is on the left, and we now need to compute this inverse solution to get back to the QSM on the right. But the math is exactly the same as in this little example I showed before. So there are a few different techniques to solve this problem. First category is techniques that use multiple orientations. So Cosmos and STI are two examples there. They are analytical solutions, and they deliver really, really good results. But the problem is they're not very practical, because we need to rotate the object of interest with respect to the field, and we need to acquire multiple orientations to the field to solve this ill-posedness of this dipole problem. Then there's also inverse filtering, which only needs one orientation of the data. And one example there is TKD, truncated k-space division. It's fast, but it needs parameter tweaking. And you can see that in the image below. When we just divide by the unregularized dipole kernel, we just end up dividing by zeros, and we get a lot of noise amplification and no usable data. So the regularization then just replaces these zeros with fixed values, and we see that the reconstructions get better. But the higher this value is, the more we will bias our results as well. So then we need to correct these results to be quantitatively correct again. Iterative methods formulate the problem as an optimization problem. So we have the estimated tissue perturbation as a forward model, and we compute an error between the measured data and our forward model. And then we have a regularization term, which we need to choose. So there are techniques like L-curve procedure where we can choose how much we want to regularize our problem, but we still have to also choose a regularization formula that we want to apply the regularization term. So these techniques are quite slow and they still need parameter tweaking. So recently, deep learning tried to solve a lot of these problems. And here I call this technique, I call this category agnostic deep learning, because these current techniques like QSMNet and deep QSM, they don't use any data constraints or data consistency constraints yet. So they just have a network, the data gets fed into the network, multiplied by a lot of filters and modified, and then an image comes out. The problem is that because there's no data consistency included, these results can be quite fragile, and it can quickly break as soon as the new input data is not anymore in the range of the training data. And in the latest category there, we have hybrid methods. So hybrid methods combine deep learning with iterative methods. And one way is, for example, predicting the output and then refining the output using a data-driven method, which would be fine as an example, or relational networks, where we take an iterative method and we unroll this iterative method and use deep learning to speed it up and get clever priors in this data. So far, I discussed these steps separately, but it makes a lot of sense to solve the background field correction and the dipole inversion in one step, as this would help with error propagations. The next slides will show some methods that do exactly that. In the iterative methods, we have the examples TGV QSM, single step QSM, and total field inversion. So they are really good techniques that combine background field correction and dipole inversion. Also, deep learning has also tried to do this. There is one technique there that's called auto QSM that combines this whole learning problem and just tries to solve the whole background field and dipole inversion in one step. And hybrid methods are also already in this space, and we present from our group one work at this ISMRM, which is called Next QSM, which is a data consistent solution for the background field and dipole inversion. Okay, now we have a good overview of which steps we need to compute QSM. In the next slides, I want to look at the bigger picture. Which toolkits exist to help us processing this data, and which methods should we choose, because there are so many, right? So some processing packages. We're very lucky. We don't have to implement all of the things that I just showed in the last slides. There are actually really good toolkits out there that have done all that hard work, and they provide it for free. So first example there is STI Suite, based on MATLAB, and delivers the Laplacian phase unwrapping, background field correction, and dipole inversion. The MEDI toolkit, same thing, has all the tools included that we need to process QSM. The fancy toolbox, also various techniques to process this data. And there is the Sepia toolbox, also based on MATLAB, which is a graphical user interface for the other toolkits. So it combines MEDI, STI Suite, Fancy, Segway, and nonlinear dipole inversion, and makes it really nice and easy to process this data. And then there's also a pipeline that we developed in our group, which is called QSM-XT. It's a complete pipeline that starts from DICOM. It also works with the bit standard. It implements our robust masking technique that we're showing at this ISMRM. We use NiPipe and TGV QSM under the hood. So it's really tweaked for high performance processing on high performance computing clusters. And we also integrated anatomical segmentation. And I hope you have time and look at this, and maybe it's useful for your work. So if you have lots of data, this could work quite well. QSM values are relative to water, and I already showed this in the earlier slides. But this causes a problem because this central frequency of the scanner depends on the scan session and on the shims and on the settings. So if we do a group study, should we re-reference our data to a common region? However, this is not that easy. The tissue we want to reference to should have a very low intersubject variance in age and pathology, because we don't want to bias our results. The tissue should also be easy to segment, because we want to have a reliable region that we want to reference to. So the quantification should be reliable then. So there are a couple of reference regions proposed. So for example, the cerebrospinal fluid in the ventricles. We can use a whole brain average as a reference, or we can use certain anatomical regions. The problem there is that it's very hard to recommend one over the other because it really depends on your research question and what particular subjects you're studying. And sometimes it just might not make sense to pick a particular region to re-reference because you don't know if this region is affected across your groups. So just coming to the bigger picture, why are there so many methods to compute QSM? And which one is correct? So we have the luck that we have multiple ground truths in QSM. So Cosmos, for example, as I said earlier, is a multi-orientation method and delivers really, really good results. The problem is if we have, for example, if you're interested in white matter anisotropy, QSM just averages, Cosmos just averages across that. So we're losing that information. So if we want to do this, we probably need to look into susceptibility tensor imaging. So we need a lot of orientations. And then STI33, for example, is the main component of this tensor. So yes, we could say these are the correct QSM results, right? But then the thing is, well, let's say we only have a single orientation. We want to do this in a clinical setting. Well, which QSM method should we use? Are some of them wrong? Are some of them better? And this is what the community tried. So they ran 2 QSM challenges with different data sets to figure out what of the algorithms out there are really good. And the conclusion basically is that, well, it depends. It depends on your assumptions. And there is, although there are clear winners in the challenges, it's not that clear, for me at least, in the field, which one is the best. And when we think about this a little bit philosophically, well, George Box and Norman Draper said something about, in general, modeling. And what they are saying is, all models are approximations. So here our QSM methods are different models and we do different assumptions. Essentially, all models are wrong, but some are useful. However, the approximate nature of the model must always be borne in mind. And I think this is quite important for our QSM methods as well. So we have different methods because they have different assumptions. And to me, all of these methods work. So in a clinical setting, they all can differentiate between bleeding and calcification. So this is easy, yes, but they will be different if you compare them because they have different assumptions. So which one of them to choose? And I don't know. There is not a clear favorite to me. However, I'm looking at the second aspect there because when we look at it, all methods are probably wrong, but some of them are useful. So let's look at it. What could be a really useful QSM method in my opinion? So to me, it should be fast, should be robust, and there should be no parameter tweaking. So maybe deep learning with data consistency gets us there. I don't know. It should be sensitive to clinical question. As I already said, all algorithms are probably doing that. The problem is just that we have that these algorithms are very difficult to use in a clinical setting. They are cumbersome, they need different languages, and it's just not so nice to use. So that is probably much harder than just getting the correct result. Then also, I think these the next QSM method should be developed in an open and high performance language. So for example, Julia, so that it can be widely used and distributed and not just based on a proprietary language. Then to me, it should have a feature that we can automatically and robustly mask brain, joints, body, or animal models. So it should have something like this included. Then also, most of the methods start at nifty files, and the scanners gives us DICOM data. So a lot of people struggle with the conversion from DICOM to nifty and then extracting the right information like the echo time and the field strength from this. So I think if we do this, we should start from DICOM. And a couple of toolboxes out there already do this. And then I think if we really want to get this into the clinic, we need to be integrated on the scanner. It doesn't make sense to transfer off the DICOM data, run to another computer, process it there, and 5 hours later get the results. This just doesn't work in a clinical setting. So if we want QSM to be in the clinic, we need to be on the scanner platforms. And then if we think that referencing and segmentation is important, well, we should come up and propose techniques to do this reliably, and also potentially come up with ways of segmenting regions of interest already in our pipelines so that people can directly use the outcome of these pipelines and can compare it to their question. So I hope this was interesting and was a good overview of QSM. I thank you very much for your attention. Thank you very much.